On August 4th, 2020, the world watched. Well, just stunned silence, really, as the port of Beirut erupted. Just this colossal explosion.
Yeah.
It was a moment that I think seared the destructive potential of stored energy into our collective memory, shattering windows miles away, leaving this lasting, undeniable mark.
Absolutely. A truly devastating event.
And that shockwave, makes you pause and think, what other high-energy cargoes are routinely passing through or stored near our bustling urban centers globally?
It's a critical question, absolutely.
Yeah.
And it's precisely what we're going to deep dive into today. The Beirut incident, while horrific, highlighted a very specific type of danger. Our focus today is on liquefied natural gas, or LNG.
Right. So our mission today is to sort of pull back the curtain on the true scale of energy on an LNG ship, then cut through some of the noise to understand how accidents involving LNG actually happen.
Which is key.
Which, I promise you, is fundamentally different from events like Beirut. We'll also explore the robust, multi-layered systems that protect us. The goal really is to leave you informed, maybe cautiously aware, but hopefully, most importantly, genuinely reassured by the incredibly strong safety practices in place.
But here's where it gets really interesting. Some might refer to an LNG carrier as a tamed bomb.
I've heard that phrase.
Yeah, why? Because when you quantify the sheer energy content, the numbers can be truly staggering. But we'll immediately debunk the implications of that comparison because the critical difference, as always, lies in how that energy is released.
Okay, let's talk about this tamed bomb analogy because it's a powerful one. It comes from the raw numbers, right? And they're striking.
They really are.
LNG is primarily methane, stored cryogenically at an astonishingly cold negative 162 degrees Celsius, minus 162.
Unbelievably cold.
A typical LNG carrier, the kind of massive ship you might see out on the ocean or pulling into a port, carries around 174,000 cubic meters of this super chilled liquid.
That's an immense volume. And if we calculate the mass using a density of about 450 kilograms per cubic meter, well, it works out to about 78.3 million kilograms of LNG on just one of these vessels.
Wow. 78.3 kilotons.
Exactly. And methane, when it burns, packs a significant punch. Its lower heating value, or LHV, is around 50 megajoules of energy per kilogram.
Okay, so the big number then. When you do the math, total chemical energy stored in a single LNG carrier.
It's roughly 3.9 petajoules. That's PETA with a P.
3.9 petajoules. Now, to give you some real context, the atomic bomb detonated over Hiroshima during World War II, that had an energy yield of about 15 kilotons of TNT equivalent.
Right, which translates to roughly 63 terajoules. Tera with a T.
Okay, 63 TJ for Hiroshima, 3.9 PJ, which is 3,900 TJ.
Uh-huh. And here's the mind-blowing comparison. That 3,915 terajoules of chemical energy in an LNG carrier. It's approximately 62 times the total potential energy released by the Hiroshima bomb.
62 times. That's a number that can absolutely make you pause and, frankly, maybe feel a little uneasy.
Understandably.
But here's the critical caveat, and this is where the analogy ends. You're saying this comparison is solely based on the total potential energy content.
Precisely. That's the absolute key takeaway here.
So, expert, this is where you tell us why that comparison is not what it seems, right? Why is it a deceptive analogy?
It's deceptive because the fundamental difference lies in the mechanism and, crucially, the rate of energy release. A chemical combustion event, like burning gas, is profoundly different from a nuclear detonation. You simply cannot equate the two based on raw energy alone. The physics are totally different.
Okay, so if it doesn't detonate like a bomb, what does happen? Let's maybe look at the Beirut blueprint again to really highlight the difference. That devastating incident. 2,750 tons of ammonium nitrate, AN, stored unsafely in a warehouse.
The mechanism there was terrifyingly specific. Under high temperatures, strong confinement being packed in, essentially, and certain contamination, ammonium nitrate can undergo what's called a deflagration to detonation transition, or DDT.
Okay, DDT. If you were to explain that in plain terms, like deflagration versus detonation.
We'll think of deflagration as very rapid burning, like igniting gunpowder in the open. A fast whoosh, lots of fire, but not quite the same shattering force.
Right.
Detonation, on the other hand, is like high explosives, C4 or TNT. It's an extremely rapid supersonic decomposition. It creates a powerful shock wave that travels faster than sound.
Faster than sound.
Yeah. Energy is released almost instantaneously. We're talking microseconds to milliseconds, creating an extremely high peak overpressure wave. This is what causes that widespread structural collapse and fragmentation. The Beirut blast, for instance, created an explosive yields estimated around, zero point 0.5 to 1.5 kilotons of TNT equivalent.
A terrifying scenario, but for our listeners, it's vital to stress this isn't how LNG behaves, is it? How fundamentally different are the risks?
Fundamentally different. That's the crucial point. LNG does not detonate in the manner of ammonium nitrate or a high explosive. It behaves completely differently.
How so?
Okay, so if LNG is spilled, the first thing that happens is rapid vaporization. It hits warmer surfaces like water or land and just boils off incredibly quickly, turning into a cold, dense vapor cloud.
Right, because it's so cold.
Exactly. Now, for that vapor cloud to ignite, the methane concentration of the air has to be within its flammable limits. The lower explosive limit, or LEL, is about 5% methane by volume in air, and the upper explosive limit, UEL, is around 15%. Below 5% or above 15%, it generally won't ignite.
Okay, so it needs the right mix. And if ignition does occur within that range, what's the most common outcome?
The most common outcome is a rapid burning, what we call deflagration. You might get a pool fire if the liquid is still there burning on the surface, or a jet fire if it's leaking under pressure like a blowtorch. These events primarily generate intense thermal radiation, extreme heat, rather than a catastrophic blast wave.
Heat, not blast, primarily. But what about this idea of a vapor cloud explosion? That sounds more concerning.
It is a less common, but potentially more severe scenario. A vapor cloud explosion, or VCE. This can happen if a very large flammable vapor cloud forms, mixes within those 5–15% limits, and then finds an ignition source in a place where the cloud is somewhat confined or congested, like around buildings or equipment.
Okay.
But, and here's the key distinction again, VCEs involving methane are subdetonative. The flame speed is subsonic, slower than the speed of sound. The overpressure generated is significantly lower and much more spread out, more of a push than a shattering blow, compared to a high-order detonation like Beirut or TNT.
Can you give us a sense of that pressure difference?
Sure. Significant window breakage might occur around 0.1 bar of overpressure. Serious structural damage to buildings often starts around 0.3 to 0.5 bar. A high-order detonation generates peak pressures many times higher than that, almost instantaneously. LNG VCE pressures are substantially lower.
Still dangerous, obviously, but a different kind of danger.
Very different. And unlike solid explosives, LNG vapor clouds, once they warm up a bit, become lighter than air and tend to disperse upwards relatively quickly. Also, neither AN nor LNG incidents produce anything like nuclear radiation. This distinction in how the energy is released, the rate of release, is paramount.
This raises an important question then. If LNG behaves differently, what can we learn from other historical port tragedies? Beirut definitely highlighted vulnerabilities, as you said, in managing hazardous substances near people. Have there been other big port disasters that, while different, offered crucial lessons?
Oh, absolutely. While the materials might be different, these past disasters offer vital context for general port safety, lessons that resonate across the board. Take the Halifax explosion in Canada way back in 1917.
Munitions, right.
Yeah, a munition ship collided with another vessel, fire broke out, massive explosion, about 2.9 kilotons of TNT equivalent.
Yep.
Huge. The lessons learned there were brutal. The dire consequences of navigational miscommunications, ships not talking properly, and the desperate need for clear public hazard signaling. People didn't know what was happening or how dangerous it was.
And then there's Texas City, USA, 1947. That was ammonium nitrate again, wasn't it, on ships?
It was. Fires on ships loaded with AN led to devastating explosions, hundreds killed. That tragedy really hammered home two things. First, confirmation that AN can detonate under certain conditions, which wasn't fully appreciated. And second, that our understanding of hazardous material risks, and frankly, our emergency response protocols were woefully inadequate at the time. It spurred significant updates.
More recently.
Well, Buncefield in the UK, 2005, that was a massive fuel terminal fire in VCE, not LNG, but gasoline from an overfilled tank. That really underscored the absolute importance of having independent, high-level safety systems, alarms and cutoffs that work even if other systems fail, and also robust secondary containment, like bund walls, to catch spills before they spread too far.
In Tianjin, China, in 2015, that seemed like a failure on multiple levels.
Tianjin was, a stark reminder. Hazardous chemicals, terminal, massive explosions caused by just blatant rule violations. It revealed systemic failures in licensing, oversight, proper segregation of incompatible chemicals, and the critical need for adequate distance buffers between hazardous sites and residential areas. It really showed you can't just have regulations on paper, they need to be rigorously lived and enforced.
So even with different materials, munitions, AM, gasoline, other chemicals, It sounds like there are some common threads, some universal lessons for general port safety that emerge from these tragedies. What stands out?
What stands out is that these incidents, regardless of the specific trigger, all point to a handful of fundamental principles. Lesson 1, know your inventory. You have to know exactly what hazardous materials you have, where they are, and how much. Accurate, accessible manifests are non-negotiable.
Makes sense.
Lesson 2, segregation, separation. Keep incompatible materials far apart. Keep highly hazardous materials away from ignition sources and, frankly, away from people as much as possible.
Right.
Lesson 3, design for failure. Assume things will go wrong eventually and build in safeguards. Blast relief panels on buildings, spill containment systems, fire suppression.
Plan for the worst, hope for the best.
Essentially, yes. And finally, robust training for emergency responders and clear, rapid public warning protocols are absolutely essential. Everyone needs to know their role.
But again, just to reinforce for everyone listening, while these provide crucial context for general port safety, they involve different materials and different explosion physics compared to LNG.
Exactly. LNG has its own specific set of hazards, and thankfully, a whole system built specifically to protect against them.
Which brings us nicely to, well, what does protect us? You mentioned the LNG industry has developed this extensive, rigorous system of layered safeguards.
It's truly comprehensive. Think of it like layers of an onion, or maybe multiple safety nets stacked underneath each other.
Okay, let's peel back that onion. What are some of the key engineering controls on the LNG carriers themselves?
Okay, well, fundamental is the double containment for the cargo tanks. These aren't just single massive containers. They have both primary and secondary barriers. Think of it like a thermos bottle design, but way more sophisticated. Membrane tanks or the big spherical Moss type tanks, they all have systems to ensure containment even if the primary layer somehow fails.
So redundancy built in.
Huge redundancy. And these tanks are heavily insulated, of course, to keep the LNG super cold. Beyond containment, these ships are loaded with sophisticated gas detection systems. Sensors everywhere, strategically placed, constantly monitoring for methane leaks, triggering alarms at levels way, way below that 5% lower explosive limit.
So early warning is key.
Very early warning. They also use inert gas systems, usually pumping nitrogen into the spaces around the cargo tanks. This keeps the atmosphere non-flammable, so even if there was a small leak, there's no oxygen there for it to ignite.
Clever. And if something does start to go wrong, like a leak or overpressure, are there automated systems?
Absolutely. That's where emergency shutdown or ESD systems come in. These are automated systems designed to react incredibly quickly. They can isolate sections of the cargo piping, stop pumps, shut valves, activate emergency vents, all automatically or with a single push of a button. And they're designed to be fail-safe, meaning they default to a safe state even if they lose power or control signals.
Okay, what about managing the pressure? LNG is boiling off slightly, right?
It is, naturally. That's called boil-off gas, or BOG. It has to be managed. Usually, this gas is either reliquefied, cooled back down, and returned to the tanks, or, more commonly now, it's actually used as fuel for the ship's engines. Very efficient.
Burns clean, too.
Burns very clean. If there's ever excess pressure beyond what the engines or reliquefaction plant can handle, it's safely vented through tall masts high up, ensuring it disperses harmlessly way above the deck and any potential ignition sources.
And the ship itself, the materials used.
Also specialized. You can't use regular steel for things holding cryogenic liquids. It becomes brittle like glass. So they use special materials like nickel alloy steels or stainless steel that maintain their strength and ductility, even at minus 162 Celsius.
So that's the hardware, but it's not just about the tech, is it? It's also about the operational protocols, the rules, the regulations.
Exactly. The hardware is only as good as the procedures and people operating it. There's a whole framework here.
Yeah.
Globally, the big one is the International Maritime Organizations, or IMO's, IGC code, that stands for the International Code for the Construction and Equipment of Ships Carrying Liquefied Gases in Bulk.
Catchy name.
Yeah. But it sets mandatory international standards for everything on these ships. Design, construction, equipment, fire protection, safety systems. It's the rule book.
Okay.
Then you have industry bodies like SIG-TITO, the Society of International Gas Tanker, and terminal operators. They develop and promote best practices for actually operating these ships and terminals safely day to day.
And at the local level, when a ship comes into port,
Port authorities have their own rigorous protocols on top of the international rules. Things like restricting LNG ship movements to daylight hours only, requiring mandatory escort tugs, setting strict speed limits, establishing temporary exclusion zones around the vessel during transit and transfer, and implementing stringent security measures under the ISPS code, the International Ship and Port Facility Security Code.
Wow, okay. Lots of layers.
Lots of layers. And all of this is reinforced by continuous rigorous training for the crew, the terminal staff, the pilots, everyone involved. Plus regular drills practicing emergency scenarios with both the ship crews and the port emergency services, like firefighters, to ensure everyone knows exactly what to do and can work together seamlessly if something unexpected happens.
Let's try and picture that. Can we walk through a hypothetical, maybe a near-miss scenario to see how all these safeguards work together in practice?
Sure, let's try. Imagine dense fog, visibility is low. An LNG carrier, let's call it the Polar Star, is navigating slowly, carefully, under pilotage towards a major city port. Escort tugs are nearby.
Okay.
On board, a junior engineer doing rounds hears something. A faint, almost imperceptible hiss near cargo tank number 3. It's a sound you'd easily miss if you weren't trained and constantly vigilant. It seems to be coming from a pressure relief valve.
Okay, what happens next? Panic. Sirens.
No panic. It's all about calm, practiced procedure. First, the bridge is informed immediately, the captain, the pilot. Speed is already low due to fog, but may be reduced further. The vessel's exclusion zone, maintained by those escort tugs, is confirmed secure. Nobody gets too close.
Right.
On deck, the relevant crew members don breathing apparatus, standard procedure for investigating any potential gas leak. They follow strict permit-to-work safety procedures before approaching the area. They use portable methane detectors.
And what do the detectors show?
Let's say they confirm a very localized concentration, maybe less than 2% LEL, right near the valve. That's well below the 5% needed for ignition, but it's definitely not zero, so it requires immediate attention.
So no immediate fire risk, but something's not right.
Exactly. The chief engineer might then order a slight increase in the amount of boil-off gas being sent to the ship's engines. This gently lowers the pressure inside tank 3, reducing the force pushing gas out of that slightly leaky valve.
Managing the pressure.
While that's happening, they prepare the relevant emergency shutdown protocol, maybe ESD1, which could involve remotely isolating that specific valve or section of pipework, ready to activate if needed. The ship's ventilation systems in that area are boosted to maximum to disperse any vapor quickly. And crucially, any hot work, welding, grinding, anything that could make a spark is automatically interlocked and forbidden anywhere near that zone.
Okay, so multiple actions happening in parallel.
Yes, coordinated actions. Within minutes, following procedure, maybe they manually isolate the valve using special tools, or the ESD system closes remote valves upstream and downstream. The repair can then commence under close supervision, maybe just tightening a fitting or replacing a seal. The portable detectors confirm the gas concentration drops back to zero very quickly.
That whole sequence.
Yeah.
That's not luck, is it?
Not at all. That's the system working exactly as designed. It shows how the multiple layers, the engineering like detectors and ESD, the procedures like permit to work and BOG management, and the human element, the trained, disciplined crew following clear protocols,